Welcome to the second part of the course about the building blocks of a quantum computer and quantum internet. The first person who formulated the idea of a quantum computer was the physicist Richard Feynman in 1981. In his talk, Simulating Physics with Computers, he postulated that to simulate quantum systems, you will need to build a quantum computer. At that time, the quantum computer was only a theoretical and nice idea, but nowadays it's a reality. Here at QTech, physicists and engineers are working together with industrial partners such as Intel and Microsoft towards the goal of creating a practical quantum computer. In part 1 of this course, you have been introduced to the layers of a quantum computer by Koen Bertels. Although we commonly speak of the quantum computer, this term is actually a bit misleading. One could better speak of a quantum accelerator. When designing a quantum computer, we try to make use of the knowledge in classical computer. We are basically adopting the same kind of layer view of what a quantum accelerator or a quantum computer will be. Let's shortly look back at Koen's introduction about the building blocks of a quantum computer.
Whenever you talk about a computer, classically we have divided that in different layers. The lowest layer is always, let's say, the hardware, the chip that has been designed. It's never a single chip or a single processor. No, it has memory, it has interconnections. So a bus that allows the processor to communicate with the memory, to retrieve instructions, and to retrieve or produce the data, that's shown here. And then it goes up to the microarchitecture that we need up to the application level. I will now go in detail on each of those layers in a quantum context, because we're basically adopting the same kind of layered view of what a quantum accelerator or a quantum computer would be. And we simply put the Q of quantum in front of every layer. And that's our research and working program. The highest level is the quantum algorithm that we know of. We don't even know yet what they will be. We have examples such as factorization, that is used in cryptography and in securing communication between machines. But quantum algorithms can as well be designing a new molecule for personalized medicine. It can be that you might want to have a climate module that you want to run on your quantum accelerator that takes all kinds of mechanisms into account that we currently are unable to compute or even model on a classical machine. So that's the quantum algorithm layer, and that's where the biggest opportunity lies worldwide, where many companies and organizations can actually start developing their own quantum application. Because every company or every end user can think of how they can use that computational aspect of such a device. One layer lower is that when you have an application that you need to program, you do that classically. Again, you have a programming language such as C++, Fortran, COBOL, or any other language that you can think of. Those languages can produce the code for a classical processor. But we also have to develop our own quantum language for the accelerator, the quantum accelerator. There are a couple of languages that have been developed so far. There's CAFCC, there's Project Q, and here at QTech we are developing our own programming language called OpenQL, which is inspired by OpenCL, which is a language developed for GPU programming. And we're now shifting it to the quantum infrastructure, so making the changes to that language. So that's the programming language layer. For every programming language, we need a compiler. A compiler takes the input of your algorithmic logic and compiles it into a lower level language that is classically called an assembly language. Again, here at QTech, we are working on a quantum assembly language, which we call QASM, which was originally developed for a book, Quantum Computation and Quantum Information, by Nielsen and Chuang, to generate the figures in their book of the quantum circuits. We just expanded that language into a full-fledged quantum assembly that is being generated by our OpenQL compiler, which is the programming language that we also developed, so that you can express your quantum logic in such a way. We're internationally collaborating with other partners working on similar things, such that we standardize this quantum assembly language. Because for now, everybody has its own local version. And that's not very good, that everybody has his own variation. But if we all agree that this is what we assume to be QASM, then progress will come much faster. The next layer is the quantum arithmetic, because the mathematics of what you need to do is completely different than classically. The quantum gates operate quite differently. That's why you need to develop the quantum arithmetic, how to do a quantum operation. I will not say anything about runtime, which is another part that we need in a quantum accelerator, because we will need it, but what kind of functionality it should have is a bit unclear right now. And that is where there's kind of the tension with the compiler development, because we still can develop a lot of things in the compiler, and maybe at a later stage we will develop that in a runtime support. All of this QASM basically maps very well one-on-one with the quantum instruction set. This quantum instruction set basically describes what the operations are that your quantum device is capable of executing. That's why we have to think of what these instructions are. So we know that classically we use an assignment like A equals B plus C, and we should be able to do something similar in a quantum device. But it's not as simple as retrieving data from a memory location and performing the addition and writing back the result, because in quantum we use it with qubits. And a qubit is a quantum bit. Classically, we reason in terms of bits, zeros and ones. And as you know, we are now using qubits or quantum bits. And they can be also 0 or 1, but they can also be 0 and 1 at the same time. And that's the famous superposition that we're exploiting in a quantum device. We can also combine two qubits so that we don't have two different states, but we have a combination of those of each qubit, two different states, namely 4 states at the same time. If I have 3 qubits, I have 2 to the power 3, meaning it's 8 states. And now it's very nice about quantum is that the quantum mechanics gives us parallelism for free, because I can apply quantum gates on those 2 to the power n kind of different states. And you will come to understand in the upcoming lectures that nothing really comes for free. There's still a lot of challenges that need to be resolved, but that's ultimately the big challenge and the big opportunity that quantum offers. And that is why you have to understand what this instruction set is and what the corresponding architecture should be. And that immediately brings us to the layer of the microarchitecture. Just like any classical processor, we have also a quantum architecture or a microarchitecture for my quantum device, which contains the processor, the memory, and also the interconnects of how the processor will communicate with the qubits. It has also local registers in the processor and an ALU, and as well as an arithmetic, so the ALU is an arithmetical logical unit, so that it can compute logical and arithmetical operations and write back the result to memory, so that the user gets an idea of what the algorithm has computed as a result. So again, here in the quantum case, we have a microarchitecture which has a similar kind of functionality. And that's the one we're also currently implementing in a real device that already controls a number of the physical qubits, the superconducting as well as the spin qubits that we're developing at QTech. For now, we're working on a 17-qubit microarchitecture, so that in principle we can go up to 2 to the power 17 parallel executions on the combination of those 17 qubits. A layer lower is the quantum to classical layer, because whatever you perform on the quantum level is always an analog phenomenon. Now you say, analog? I thought we were building a computer which should be digital. Well, everything up to the microarchitecture is clearly digital. But ultimately what you send down to the quantum chip is, for example, a microwave. It can be other things, but let's say it's a microwave. And we control an individual electron, an individual collectron at the atomic level. And the individual electron is important to understand. So if I have 17 qubits, I basically have 17 electrons. Not 100,000s, not millions, but 17. And there are ways to combine those 17 electrons and their spins in a way that they interact and move that indicates that they are doing a particular calculation. So that means that this layer is necessary for translating all of the logical steps that you need to do in your algorithm into the appropriate microwave or the physical signal that you want to send to this electron and to the qubit. And then ultimately it enters into the quantum chip, which consists of these qubits which are connected to each other. And then we hope, of course, that we get a meaningful result. Now, it's nevertheless important to understand for a quantum accelerator, for any computational device, is that it is a non-deterministic way of computing. That means that it is not like in a classical machine that you run 1,000 times exactly the same algorithm and you will get 1,000 times exactly the same result. Quantumly, this is absolutely not true, because when you want to read out the result, several things happen. And the most important is that any entangled superposition that exists actually is going to get destroyed. So if I have, for example, these 2 to the power 17 possibilities, I'm only going to get one of those possibilities back as a result, and all the others will disappear. And that's why you may have to do a computation 10 times, maybe 100 times. We don't even know how many times we need to do that. And then you can make a histogram of what has been computed, and the readout that has the highest frequency of occurrence has a high probability of being read out by your microarchitecture. And that is what we can report back to the end user. So that's something you should not forget. A quantum device is a very powerful device. It gives massive parallelism in principle, but we need multiple runs and average out what those calculations of those results are. And the one with the highest frequency is the most likely result of your quantum device.
In the first part of this course, we took some time to introduce you to quantum materials and Ket notation. We talk about the basic unit of information in quantum computing and quantum internet, the qubit. Let's have a look at the 4 types of quantum platforms that has been discussed.
In the first part of this MOOC, we mainly focused on the lowest level, the quantum chip that forms the foundation. The quantum chip is the quantum circuitry hosting the physical qubits. Physical qubits can be controlled to a superposition state and coupled together to create entanglement. These principles are on the basis of a quantum computer and quantum internet. The quantum mechanical state of a qubit is usually fragile and can suffer from environmental interactions and decohere over time. However, in order to do operation on these qubits, it is essential that many operations can be done within the qubit coherence time. Theoretical predictions state that for practical, fault-tolerant quantum computing, it will be necessary to perform thousands of operations within the qubit coherence time. While more sophisticated quantum error correction protocols are actively being studied, it is clear that good qubits are essential and that qubits need to be of high fidelity. Today, various qubits are being explored and investigated to reach this goal. In this series of lectures, we have introduced to you several of the most promising qubit systems. Qubits based on the spin states of electrons or nuclei associated with defects or donors in silicon or diamond can reach very long coherence times. In materials with low net nuclear spins, detrimental magnetic interactions with the environment are small. In addition, the strong confinement leads to small overlap with other states. And these centers in diamond are particularly interesting as they can be coupled to photons, providing an optical link between spin qubits that are distant from each other. Spin qubits and quantum dots also exhibit very long coherence times, but they also offer the advantage of being man-made. This allows to realize qubits at a predefined location, which is clearly beneficial for scaling up the number of qubits. Superconducting transmons offer this advantage as well. In addition, they are larger, and so, at least in the few qubit regime, it is even easier to fabricate these types of qubits. Large efforts are devoted to improving the qubit environment, leading to qubits that become more and more isolated, and thus to qubits with extended coherence. This is achieved by, for example, removing magnetic noise from nearby nuclear spins, or electric noise stemming from charge defects in the substrate. In addition, clever qubit designs enable to decrease a qubit sensitivity to noise. For spin and superconducting qubits, sweet spots exist where to first order qubits are insensitive to certain noise. A special class of qubits exists that can be made intrinsically insensitive to some noise. These are called topological qubits, and are qubits such as the ones based on emergent Majorana fermion states. These qubits could become exponentially less sensitive to local noise with increasing system size. That is, by increasing the separation between Majorana fermions, the qubits become more and more protected against local noise and can thus hold their coherence for a longer time. Today, we do not know what the best qubit platform will be, and so there's an active race going on between all these different platforms.
But how do we go from quantum hardware to a quantum computer? In this second part of the course, we will introduce you to the other layers of the quantum system stack. We will also talk about quantum internet. At QTech, the Quantum Internet and Network Computing Group is working on realizing a quantum network that connects 4 different cities in the Netherlands. I hope that you will enjoy this course and it becomes clear that building a quantum computer and a quantum internet requires different expertises, such as physics, mathematics, and computer and electrical engineering. Good luck!